Hello, I'm Justin alongside Team 9 consisting of Emma, Rachel, Nick, Julia, and Allison, and we will be redesigning the Hoover Wind Tunnel Air Vacuum Model UH70400, and more specifically the vacuum head subassembly. To give a little background about the product, it is a typical household vacuum and is useful for cleaning dirt and other debris off of carpets and other surfaces. It accomplishes this by creating a vortex inside the canister to suction off the debris from the surface being cleaned.
Seen here is an exploded view of the bottom portion of the vacuum, the area of interest for our redesign. Seen in the bottom left of the image is the sole plate, and to its right is the roller brush it houses. In the top right corner, the two trunnions can be seen. Trunnion 1 houses a switch that determines the position of the vacuum, and Trunnion 2 houses the vacuum's power cord.
Our primary customer group would be homeowners or home renters who have larger areas of flooring that need to be cleaned, and this is typically done with more frequency and regularity. And our secondary customer group would be college students or apartment renters who have smaller floor areas that need to be cleaned and are typically on a tighter budget. For our functional analysis of the vacuum head, our primary function is to guide the vacuum. The secondary functions can be broken up into focusing suction, lifting dirt, and moving the vacuum. Lifting dirt is also broken down to adjusting the suction as well as contacting the floor. To assure convenience, our vacuum head must also be able to stand upright and be rapidly deployable.
There are many options for assembling the head of a vacuum cleaner. Our group decided upon two distinct possibilities, which are drawn out here in fishbone diagrams. Both sequences begin with the base plate as the starting part. The first sequence then attaches a subassembly composed of the sole plate wheel assembly, roller brush assembly, motor assembly, and belt. Then the cover plate is attached, followed by the upright lock, first trunnion, second trunnion, wheel bearings, axles, and finally the wheels. This sequence only has one subassembly because it is rather simple to attach the wheel axles and bearings directly to the part at the end. However, the second sequence has combined the wheels, axles, and bearings into another subassembly to allow for the subassemblies to be completed in parallel. In analyzing our assembly sequences, both sequences were similarly easy to transfer or handle, similarly easy to locate all of the parts, and similarly easy to fasten or join. However, when it comes to subassemblies, sequence 2 was easier to test subassemblies, and for assembling in parallel, sequence 2 was the only sequence that was able to be assembled in parallel for multiple subassemblies. Therefore, sequence 2 was easier to assemble with a total of 15 versus sequence 1's total of 12.
Here we see the function component mapping matrix, which is used to realize which components cover which function, as to not include unnecessary parts in the assembly. The functions are from the FAST diagram, and the part numbers are from the fishbone assembly sequence. So we can see here that each part has a function, and each function is covered by a part, and so there are no wasted parts in the assembly.
This is our bill of materials. We estimate that the cost of producing one unit will be $24.54. Some assumptions we made when calculating this value were that the production volume will be 20 million units per year, the labor rate is $15 per hour, and we calculated all injection molding costs based on volume of each piece and the standard injection molding rates. We excluded costs of manufacturing any electrical components for simplicity, and we found that standard retail cost is $190. Thus, the cost to produce one unit would be 13% of standard retail price.
Here we compared how each product function differs between our customer groups. We grouped the functions based on those that are the same for each customer group and those that are different. You will notice that the pleases senses is listed in both groups. This is because both customers will require a product that pleases the senses, but our primary customer group, homeowners who clean regularly with a vacuum, may require a more aesthetically pleasing design than our secondary customer group, college students and apartment renters. There are opportunities for changes that we can make that would appeal to both groups, and changes that would appeal to each customer group differently. Next, the product components were sorted based on whether they are a platform or can be varied as a module. Many of the platform parts are internal parts, as you can see, whereas the modules are largely external components and can be varied to fit each customer's needs, budgets, and aesthetic preferences in order to optimize the product for each customer group.
One redesign implemented in both the primary and secondary designs is the reduction of the number of bristles on the vacuum's roller brush. This change was adopted to reduce the amount of time the consumer spends removing debris like pet fur from the brush, as well as lowering the material costs of the part. One of the design changes made for the secondary customer group was reducing the size of the larger trunnion hinge in the rear of the vacuum. In making the left hinge identical to the right hinge, The tooling cost of each part is significantly reduced, lowering the cost for consumers seeking a less expensive option. This also eliminates the switch in the secondary design, as it is not essential for the vacuum to function. Finally, the slots in the casing for the roller brush assembly were reduced from 5 segments to just 1. In doing so, the tooling for the part is less complicated. This design also cuts back on unnecessary material, lowering cost and waste.
When taking into account our redesigned features, we decided to also rethink our assembly sequence. We took our better assembly sequence and manipulated it to increase the ease of parallel assembly and allow for product differentiation to occur later in time. Because our primary redesign includes a change to the roller brush assembly, and our second redesign includes a change to the sole plate, we separated the sole plate assembly from the brush assembly and moved both further down the tree. We also switched the position of inserting the motor assembly and the roller brush assembly so that the roller brush would be inserted after the motor. Finally, in both our primary and secondary redesign, the trunnions occur as the very last step to ensure maximal time before part differentiation.